I would like to now discuss linear and angular speeds. Consider the drawing that I have here to the side. What I've done is I've formed a center point in the middle of my circle, and I've extended a segment out to touch the outside of my circle, and I've placed a point there. I think of that as my initial side, and then I copy that side up to a terminal side, and I have rotated through a certain number of degrees or radians. I want to think about two things. I want to think about the rate at which this point is moving along the circle. I'll call that point P. The linear speed represents the rate at which a point moves around the circle. So however fast this point P is traveling around the circle is called the linear speed. The other thing we're going to consider is angular speed. Angular speed represents the rate at which the angle changes as I take this initial side and I rotate it around. And so angular speed is the rate at which my angle is changing. Now, this being the case, I need formulas for both of these two topics. Linear speed is denoted by the letter V, and the formula for that is arc length divided by time. Okay, the arc length we know has to do with the distance between points on the circle, and so the distance is divided by the time, and that'll give us a rate. We know a formula also for arc length. S is equal to R times theta. And here, for the linear speed, that would be divided by t. You can use either of those two formulas to find your linear speed. Angular speed is denoted by the Greek letter omega. It's like a little W, and this is equal to your theta divided by t. Now, for both of these two formulas, make yourself a note. Theta is measured in radians. If it's not measured in radians, then you need to convert degrees to radians. Now, I'd like to look at an example of these two topics. Okay, my example says a Ferris wheel has a radius of 30 feet, and it can make one revolution in 70 seconds. Okay, the first thing I'd like to find is I would like to find its linear speed. Now, if they don't tell you a unit that they want linear speed in, what you do is you assume it's in the units that they've given you. So in other words, you see here that they've given you 30 feet and they've given you 70 seconds, and so linear speed is going to be in feet per second. If I want a different unit measure, then I will give it to you. Okay, I will ask you, I want linear speed in miles per hour or something along those lines. Okay, the formula for linear speed, we say it's V equals S divided by T, or R times theta divided by T. We'll look at this information and we'll see what we've been given to figure out which formula to use. Okay, from here, you all agree that they haven't given us any kind of an arc length, so it's probably better to use the second part of that formula. They've given us a radius of R, they've given us a time measure of 70 seconds, they haven't straight up given us a theta measure. Theta needs to be in radians, and I don't see anywhere it says that this is rotating through however many radians. But they actually have given you that information when they say that the Ferris wheel can make one revolution in 70 seconds. One revolution is equivalent to 2 pi radians. So on here, I'm going to write down 1 revolution is equal to pi radians. And so they actually have given me the angle measure. So let's go down here and let's fill in what we know to find the linear speed. R was 30 feet, and I'll go ahead and put the units with this. Theta is 2 pi. Okay, if theta is in radians, I won't put the unit measure with it. If it is in something different, I will put the unit measure with it. Okay, the time was 70, and that was in seconds. So on the top, what I have is I have 3 times 2, that's 60, but I also have the pi there with it. So this is 60 pi feet divided by 70 seconds. Okay, that would reduce to 6/7 pi feet per second. And so that would be my linear speed. Let's now go and find the angular speed. Often, for angular speed, they ask you to find the angular speed in revolutions per minute, or revolutions per some time measure. This particular problem is easy to think about because they actually told us that you go through one revolution in 70 seconds. So they have essentially given us this angular speed, but do notice that they're wanting it not in feet, but they're wanting it, they're wanting it in minutes, not seconds. So on here we'll have omega equals, and then we have theta divided by time. On this particular one, we're going to go ahead and convert theta to revolutions because they gave that to us already. And so we would have in here that this is actually just one revolution per 70 seconds. The only thing that we really need to change is we need to change the seconds to minutes. So I'm going to come over here and I'm going to multiply. I need to get rid of my seconds, and so I'm going to put 60 seconds on the top, and then I'll put on the bottom 1 minute. And that will get my time units in the proper measure. The seconds you see will cancel out. On the top I'll have 60 revolutions per, on the bottom 70 minutes. And then that will reduce down to 6/7 revolutions per minute. And that's my final answer for angular speed. I could have also done this angular speed if they had asked me, I want the angular speed in radians per minute. What I would have done there is, instead of doing one revolution on the top, I would have done 2 pi radians on the top and then gone from there. This concludes the lesson on linear and angular speeds.